Okay, so the topic of this video is some more practice where we're going to work now some concepts we've been doing in the last few videos. So we're going to talk about, with these problems, it's going to be equilibrium and some moments, some center of mass, maybe, and some rule of moments. All right, so that's the topics for this. Let's just jump right in. All right, first problem we're going to look at here. It says a simple balance has two pans suspended from the ends of arms of equal length. When it is balanced, the pointer is at 0. So you've got a beam here. It's hanging from this pivot. These arms are equal in length, so the whole thing can rotate. Basically, it can go like that, rotate that way, or it can go like this, rotate that way. All right. The pointer here will then move. So it'll either move this way or it'll move that way depending on the masses, whatever you put in these two pans here. All right. It says 4 masses are placed on the pans, 1 or more on pan X and the others on pan Y. All right. So which combination of masses could be used to balance the pans? All right. So we have 4 possible combinations. So at least one has to be in pan X and at least one in pan Y. All right. So basically we're looking at these combinations of masses and we're seeing if there are any combinations we can put together of these different masses that would be equal. Right? So we need an equal number in both pans. All right. So a good place to start would be see what your biggest number is and then see if any of the other numbers could add up to it. So let's start here. We have 10 and then we have 5, 1, and 1. You can see it already right away. 5 plus 1 plus 1 is 7. You can't get up to 10. There's no way you could balance those pans with this one. So it's not A. All right. Letter B. Our biggest one is 5. So if we take 1 plus 2 plus 2, that's 5, isn't it? So if we put 1, 1, 1, 2, and 2 there, and then we could put 5 there. Although I probably did that backwards. I think we were supposed to... Anyway, it doesn't really matter. You put those 3 of those masses, 1, 2, and 2 on one of the pans, 5 on the other pan. Bam. Those add up to 5. This is 5. It would balance. Alright? So the answer, we just stop right there. The answer is B. Okay. Moving along. What are the conditions for equilibrium? Well, this is really just a definition, so it's a question of whether you remember what are the conditions for equilibrium. Is there a resultant force, and is there a resultant turning effect? And the answer to both of those questions is no, there is not. So we're either here or here. Can't be either of those first two because there is no resultant force. All right, resultant turning effect, no. So here we go, letter D. Letter D. All right, here we have a question about center of mass and also how that causes moments. So here we go. We have 4 models of buses and they're placed on ramps that are tilted at different angles. Right, the center of mass is marked on the bus. Basically, they're the same model of bus in 4 different situations. Question is, how many, if any, well, how many, because at least one, they don't have 0 as an option. So how many of these models will fall over? So the question then is one of stability. Okay, so this is maybe a little bit of a new concept. But an object is stable and it will not fall over if its center of mass is above something that supports it. So in this case, the support would be the wheels. Okay, so then if you draw a straight line down from the center of mass, if it's at or between the wheels, then it is stable, it will not fall over. So this first picture, it's fine, it's not going to fall over. Next, straight down from there, alright, didn't quite get that straight, but you can see it's still between the wheels. That one's not going to fall over. Okay, this one, I messed it up in the end there, but you can still see. That one is at the wheel, but it's not outside the wheel. Alright, so it's still over the wheel. This one should be fine. It should not fall over. This one, I probably exaggerated that a little bit. But that one is not between the two wheels. Alright, it's outside of the wheels. There's nothing to support this thing. The center of mass is outside of its base of support, so it will fall over. Alright, so how many models will fall over? Just that one, this last one over here. Okay, that one's going to fall. Alright, moving right along. A wooden plank rests in equilibrium on two boulders on opposite sides of a narrow stream, so boulder 1, boulder 2. The question is, how are these three forces related to each other? So this is the force of weight of the plank, and then these are the reactive forces, the upward forces of the rocks that are holding the plank in place. I should point out that these arrows are not drawn to scale. All right? So what is the relationship between these forces? Well, in equilibrium, no resultant force, right? No resultant force. So we know that there's no resultant force. I'm sorry, my handwriting is awful. We know that there's no resultant force. So what does that mean? It means that the total upward force has to equal the total downward force. So F upwards equals, wow, that was awful. Okay, let's try that again. FV for vertical is equal to FD for downward. We're going to say vertically upwards. Alright, just so I can abbreviate this. So the total upward force has to equal the total downward force. There's only one downward force, so Q belongs by itself on one side of this equation, which already shows you the answer, because here Q is added to P, here Q is added to R. It could be C possibly, but Q has to be by itself, alright, and not added to anything, because Q is the only thing going downwards. P and R are both going up. Anyway, to cut a long story short, there we go. P, upward force of P plus R has to equal the downward force of Q. Alright, two more things really quick. Let's zoom in on this. Alright, we have 4 planks, each of which is identical. And then we have 2 equal forces acting on each plank, 2 equal forces F. So all of these Fs are equal to each other. They're all the same amount of force. So the question is, which of these planks will turn? Alright, which one will turn? That's the question. Alright, so here we have this force upward that's going to cause a clockwise moment around the pivot, and this force is going to cause a counterclockwise moment around the pivot. So this one will not move, or possibly if the pivot is not attached, then this whole beam is just going to lift up. Here, so this one will not turn. Not going to turn. Alright, next. This downward force is going to cause a counterclockwise moment, anti-clockwise. This one will cause a clockwise moment. They're equal distances from the pivot, so that one's not going to move. Here we have a force downward and a force upward. They're acting at the same point and they're equal, so these are just going to cancel each other out. And that one's not going to move. So that leaves us just this one over here, and we'll explain why. Alright, this one is causing an anti-clockwise moment. That one's causing an anti-clockwise moment. Nothing is causing a clockwise moment. Therefore, you will get a turning effect on that one. Okay? Last thing, we're revisiting a problem that we looked at from the video on the rule of moments. So we've got this thing here, and it's a disc. It's a circular disc with some holes, and we've hung 2 masses from it. Right? It will balance because this mass here is half the mass of that, and it's twice as far away from the pivot. So that means that the moment caused by this one is going to equal the moment caused by this one. This will cause an anti-clockwise moment. This will cause a clockwise moment. The thing will be in equilibrium. Nothing's moving. But what do we want to do? We want to calculate the moments. All right, that's all. So the moment due to the first thing, all right, first step, we need to find weight. So weight is equal to mass times g. So the weight of a 200-gram mass is going to be 0.2 times 10, which is equal to 2 newtons. All right, 2 newtons. And then the other mass, 0.4 kilograms times 10, is equal to 4 newtons. All right, so those are the weights of those masses, okay? So that's step one. Now that we know the weights, which is a force, we can calculate the moments, okay? So the moment is equal to force times distance. All right, so the moment for number one would be 2 newtons times 8 centimeters. So that's going to be 16. I'm going to move over. 16 newtons times centimeters for number one. All right, and then for number two, let's scoot ourselves over here. I'm just going to use little m to mean moment. I'll use MOM. Moment is equal to, and let's go back and check. We've got 4 newtons, and it's 4 centimeters away from the pivot. So 4 newtons times 4 centimeters. You'll notice that's 16 newtons times centimeters. How about that? It's the same. You see that? 16 newtons times centimeters, 16 newtons times centimeters. That's the same value for the moment in each case. That is proof. Well, basically calculated proof that there is no moment. There is no moment, there is no turning effect. No resultant turning effect is acting on that disk because you have a clockwise moment that is caused by the first mass. This one causes a clockwise moment. The second mass causes an anti-clockwise moment, and they cancel out. As you can see, they're both the same size, and since they're in opposite directions, they will cancel out, and that means there is no net moment on this disk. The disk is in equilibrium. It is not moving. Sweet! Alright, thanks for watching.